I should have been recording the NetHack. That's what I should have been recording.
Yeah, maybe you can do a short little special of it on YouTube.
Yeah. And live transcript, which will be enabled. And now let me turn it off because I don't want to see it. All right. So,
Professor,
here we are.
A silly idea is that if at some point you're bored, you could say, I'm going to be live streaming NetHack on Discord.
People, now there are special quests you could do in NetHack. You can see if you can do a speed run with the minimum number of moves, which is insanely difficult. You can see if you remain vegetarian, avoid eating any monsters, which is a real problem because monsters give you benefits when you eat them. And I think we were working on Flipbit. Were we working on Flipbit?
I believe we got to, I think we finished Flipbit, and now we're on to Is Little Endian.
Okay, we're going to skip Little Endian. Let's go on to Is Power of 2, because that is embarrassingly easy, but it's going to be hard because you don't know how to do it. All right, now let's see. I had some code. Yeah, all right. So let me uncomment out my testing.
We're still on the GitHub.
All right. And I'll be on the GitHub in a moment. I'll be back in a moment. Let me just get the Is Power of 2. Let me just get all of these, be done with it. And now here. And okay, everybody, have at it. Do those.
So in order for something to be a power of 2, it has to be, there can only be 1 1, and everything else has to be 0. Except the first one, because no, that'd be a power of 2. You guys see what I'm saying? Jordan is talking.
Yeah, keep talking.
So okay, okay. But yeah, in order for something to be a power of 2, it has to be, there can only be 1 1, and everything else has to be a 0.
Okay. So what can you take advantage of? And this is going to be another one of those one-liners. No asserts in it.
We'd need to do maybe an XOR statement.
Well, get out a piece of paper and a pencil and try and work this out.
Well, to be fair, up until Tuesday, I've never used bit operations.
That's why I love this class.
When you mentioned, oh, you guys have used these in the previous course, well, I thought you were talking about if-then statements. In which case, yes,
I'm gonna go get another laptop so I can see you all and get you off my screen so I can put you on that screen. I'll be right back. But keep talking.
All right. Blah 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 blah. I know.
Not helpful.
Yes, indeed. We are going to want to turn. Is that power of 2 is just like means it's divisible by 2, yeah, or no?
No.
Aren't the powers of 2, it's like 2, 4, 8, like that kind of thing?
Yeah.
Be represented by 2 to the n.
No, I think Jordan's
Correct.
Jordan was
Meaning
right earlier.
that there can only be 1 1 and the rest are zeros.
Yes.
So if we use that and we figure out how to confirm that there's only 1 1 and the rest are zeros, then we can have some fun.
I would want to say that Nah, no, just doing a if the thing is has a remainder of 0 when compared to 2 probably wouldn't work.
Check if the first bit is 1.
We could do that, but then how do we check to see if like the second bit is 1?
Yeah.
Does
Doesn't matter.
Yeah, it does. Because 4 is a power of 2. 8 is a power
Yeah,
of
I
2.
suppose.
16
I
is a
mean,
power of 2.
See, you're not wrong. That's just one case where we could do it.
Shift,
So
We have to do one.
shift until you get to the last one, I guess.
We can't. We don't have any number of bits, and we can't use any loops
Um,
And no if statements.
and no if statements.
that's
It has to be one line using the bitwise operators.
Ew.
Yeah. So
If we
Well-
do exclusive OR,
Do we first want an assert statement to verify?
no,
that-
the professor said we don't need to use an
Oh,
assert
okay,
statement
okay.
for
I'm
this.
sorry.
because we're only given the bit or the binary number per se, so there's nothing really to assert.
Oh, okay.
Mm-hmm. Like we can check if it's a number, but not much else.
Well, I mean, everything's represented in binary, so a letter could be
Yeah.
a number. So that would just be useless.
I'm just making so that this will compile. Okay. That should compile now.
So
I think we can just completely ignore the shifting because we have no way of shifting by a certain amount.
yeah, because we might get out of bounds. I would agree.
Yeah, I mean, so we can kind of just realize that shifting is probably not going to be the answer. So then we have and, or, and exclusive or.
Like the and statement is interesting to me, as this two things have to be true in order for it to be true. It was what I'm getting from that, but I don't think we have two values to use, so that would take the and statement out.
You can make a value.
Yeah.
Should we
Wait, what if
compare a
we-
value
Why
that's
don't we
completely
compare
ones
it-
in binary, and then compare that with an and to see if any of the results is like a 1 from the V, and then a 1 from the all one binary value will result in a 1 from the and that would mean that there is a 1 inside the original bit.
Can you say
Like
that?
if you anded, so say we're sending in V. If you anded a 11111111, if you anded those two together and then look to see if there's a place where there's a 1 in the V value and then also a 1 in the binary number you just made, then that would mean that there's a 1 at that location. I just don't know how we would isolate
true.
looking for just a single 1.
Wait, we can figure out how much we can shift. Just take
Just
size
use
of
the
V.
size of, yeah.
Although he says it's one line, so
But
I-
how's that going to help? All right, so let me start up my calculator.
Don't you like-
And,
and it with 0.
that's going to make 0.
Yeah, because all of them.
Yeah.
would be-
In order for and
Or
to
it with
become
0.
one,
Or wait. What if we exclusive or with 0?
then that would give us a 1 in the place where there is,
A 1.
yeah. But then we'd be kind of back.
But yeah, I see. No. Because you would still, yeah. Um,
All right, so there's 128. So you see, you got one bit on. How about 1024? Well, let's get rid of everything. 1024 is a power of 2. Yeah, there's just one bit on. Let's see, hide binary, show binary. Where's the, oh, okay. So there's the binary. Got it. It's just really small. So there's a 1 over in that position right here where my cursor is. All right, well, running out of ideas?
We basically have.
Well, I wonder what would happen if you subtracted 1. Okay, now it may be small, but I want you to look here. Can everybody see that?
Mhm.
Let's
Yeah.
put in 400 hex again. And I'm going to leave my cursor underneath the only 1. Now subtracting 1.
So, oh. I didn't know we could do mathematical operators. I thought we had to use exclusively bitwise operators.
Okay, well, you can use mathematical operators and carry on. Carry on. Bring it home for us, Jordan.
So if we subtract 1 from V, and then we do, I had it and then I lost it.
Well, let's try a different value. So let me go back to base 10 and let's see, 1,000, 1,000. Does everybody agree that's not a factor of multiple of a power of 2?
Yes.
Okay, so look here. And I'm going to subtract 1. And I still got, notice that I have zeros down here. But when I did it with a power of 2, it was consecutive 1s.
So if we
So
flip,
that's
if
my
we do
hint.
-1 and then we flip the signs, no, because that'll just give a 0.
That'll only give us 0 if it's a power of 2.
Yeah. So I guess we say if we take V -1 and then we AND it with 0, if that is equal to 0, then it's true.
Boy, the wheels came off the wagon there. You were on a good track. Okay, so how about V ANDed with V -1? And one more thing. What will if this is a power of 2, work it out. What's that going to return?
Well, if everything is set to 0, it's going to return false, right?
Okay.
So we're going to want to return not V.
There. How's that?
You forgot one extra parenthesis at the end. Or not. Never mind.
Would you just do the opposite? Are we allowed to use that exclamation?
Never said we couldn't.
It's
Yeah.
a not.
I
All
mean,
right,
it
let's
makes
try
sense
this.
because it's a bool. It's a logical operator, so you could use the exclamation point.
All right. And let's see, which line are we looking for? We want to be testing line 57 and 58. Okay. So
Alright.
true, expected
be-
true.
To be fair, what I said earlier was basically that.
You didn't
Yeah,
use
it
the
was
correct
basic.
syntax.
It was
Oh, but
extra
then
steps.
Yeah, but you were anding with 0. That's where the wheels came off the wagon.
Yeah.
All right, so let's do the next one, only with int64s, and then we'll add a template to it. Is same size. Same sign, sorry. That's an easy one.
We just do is thing equal to the second one.
What bit is it again? That's the sign.
No,
It's like
it's the
31.
first.
Due to's complement for this. So flip the zeros and ones and then add 1 to it. And then I'm forgetting what number you're supposed to look at.
Or we could just have them.
Can we look at the sign bit?
Yeah, we just
That's what
have
I
to
was
look at the sign bit.
Oh, is that all?
Yeah, the
Yeah.
sign bit's like
We
what,
just
31. So
We just need to see if that bit is the same. So we just use an equal to statement.
Okay.
But how do we look at a specific bit?
Just
Is the question.
shift it by the
I
appropriate
don't know,
amount.
you've been doing that all along.
Are we given bit num?
No,
I
but
mean-
we're looking at a set location.
yeah, because it's always gonna be 30.
So yeah, but think about it. I mean, we
or
could do it
60.
for
Oh, it's
64.
64. So it's actually that's 63rd bit, right? You have to shift
Mhm.
63. So
All right,
that's
so
what.
how about this? How about A and 1 shifted 63? How about that?
I would say so.
Yeah.
If you don't want to use the equal sign, we could use an and there.
Yeah. But so how would we do this templated if we can't use size of?
We
But-
can
but
use,
We can use size of? Okay, then we do size of.
But we also already know
Alright.
that we're gonna pass a 64 bit integer, right?
Yeah, this one is not templated. The rest, like all of
But-
them but 2 are.
But we do have to
This one.
convert into template. He did say that.
all right.
Oh,
But
Yeah,
it's
let's
not
convert
it's
it
not
to a template.
declared. Okay. Well, now we do, but it
Yeah.
wasn't declared as a template class.
Yeah, now the
But that
problem
would be a
here is if you
trivial
were
difference.
defining this. Yeah, however, you need to understand the following. Right? If it's an unsigned, you don't have a signed bit. That's what we're leveraging here. So as the designer, you'll just have to figure that out. Now, how many?
But I mean, why
bits
would you
have
check
to-
the sign of something if you declare it specifically unsigned?
This would require an assert function to detect if it's unsigned int or something else.
Well, I don't know how to template and then test what the type is.
I don't think you can do
Okay,
that.
but that would.
So I mean,
Yeah.
So I guess correct me if I'm wrong. I was under the impression that like unsigned was basically just always positive, just because
Mm-hmm.
it never sorts. So wouldn't there be a signed bit, but it's always positive? I forget if that's like 0 or 1, but
No, all of the bits are
get
used
to
to
use the
represent the
sign
number.
bit. Right.
oh, so it's like used for the actual numbers now instead of signing. Is that
hmm
okay?
That's why you get, I guess, twice the amount of values in an unsigned int. Well, you can store higher values.
Yeah, okay.
using negatives.
That would make sense.
All right, what do you think of this?
It's good, but again, with the it would not work if it's signed or if it's unsigned.
Right. So you document that. That's what documentation's for.
Oh, okay. I thought you were wanting us like this function has to work for everything. I see.
Mhm.
It would execute, right? It just wouldn't tell us anything that's useful, but it would be able to execute.
Correct. Correct.
Is there a specific reason why you call it mask?
It's a bit mask.
That's the historical correct term for what it is. It's a bit mask. I'm masking out all the other bits. All right, well, let's try that. And what are we supposed to see? We're looking at line 62 and 63. And well, looks like it works. 62 and 63. Okay.
Did
Now,
you
is negative? That's trivial.
Yeah, we just checked to
Did I
see
what?
if it's 0 or 1 at the signed location. And we
Right,
just
now
basically
I'm
did
gonna leave
that.
Okay, so tell me how to do it.
We would check at bit 64, or we would return, well, we can't use an if statement. So we would need to shift 63 bits over.
size of t times 8 minus 1? Because we don't actually know.
Yes.
There you go.
Beautiful.
All right, and let's see, we're going to be checking 64 onward. Okay, everybody is lining up correctly.
Woohoo!
All right, this is
Yeah.
bit bashing.
We have one more though.
Yeah. Oh, the is little.
I'm
Okay.
reasonably certain I completed this correctly.
Right, because we did see it as part of the discussion in the last class.
So my implementation said so I made an unsigned short, or just to get what its natural thing is.
Zachary. She is.
Okay. So
Yeah.
I've included this, Cephas, so let's not use unsigned short, all right? Let's use the exact, which would be a U int 16 type. How's
Sure.
that?
And then
What do you want that to be?
I'd set it equal to 0x FFAA.
All right, is equals 0x FFAA.
And then
So you're making a pattern that you can recognize in the first byte and the second byte.
yes, that's the plan.
Okay, good.
And
What's
then
next?
I'm reasonably certain I need to use, I think you just use an XOR to make sure they're all the same. So you compare it to the pattern. So I said, if it's return 0x, so if I'm going to shift it to the right by 8 bits. So we're just going to isolate the FF, right? The FF part of it. Do you sort of see where I'm going?
Well, I think so.
So I said return 0xAA. And I think I actually wanted to do a NOR operation, but I didn't quite get that working. Or XNOR.
So you don't have this working.
Sort of. I have like, I analyzed all of my shifting, but I can't get, how do you compare if they're the same such that it returns 0 if they're not the same and 1 if they are the same?
Oh, you make me so sad. You're
Be
making me
sad.
very, very
Be
sad.
sad, Dr. Kavolowitz.
Yeah. Go with it. Feel with it. Sit in your sadness.
Exactly. Embrace the shadows.
Mm-hmm.
That well, my shift bits are correct. I'm just not, I don't quite remember how to do the comparison thingy. So if you tell me that much,
Okay.
I'll be correct. I would have
What
figured.
is your question?
What if you just did 0x1, shift it right once and see if that's 0?
No, it has to be between multiple bytes. That's endianness. It's not within a bit or within a byte, I guess.
Oh, okay.
You need at least 2 bytes to get endianness.
Okay.
Wait, you can just say equal equal? I'm an idiot.
Yeah, that's
Wait,
why
I thought we
sad.
had to use the operators or whatever.
We can
use
use
That
equals.
equals right there.
We've been using equals to a few
I
times.
implemented this before this class, by the way, remember? So I didn't see all this.
Well, what did we learn today?
Use other operators.
Never assume before class.
Spell it out for us. Spell it out.
In
for
any
us.
case, so return 0xAA is equal to S right shifted by 8, or V, you called it V.
All right. Read it again to me.
This is what I'm reasonably certain this is the case. 0xAA is equal to S right shifted by 8. At V, I think.
Okay. So,
Or it might be 0xFF.
well, once a value is in a register, should it be in the right bit order? Let's see.
When I looked at it in LL, in GDB or whatever it is, it seemed to not be, but that might not be in a register. Your machine
Is this
is little
machine-
endian, right?
Well, it's saying it's false. So, which is it?
Well, or can you say for certain your machine is little endian? Like, you know that just for certain?
Let me look something up first so that I make sure I got it right. What am I looking for? Let's try here. Where did I put this? And I'm gonna show you how I did it. Where is it? Am I just not seeing it? Oh, there it is. Okay, now figure this one out with me.
So you're converting, or you're taking a char star, which is 64. No, yeah, it's 64 bits.
See, Cephas, where you were going wrong is you have to test this the way it appears in memory. Go ahead, Jordan.
You're checking to see if that matches pattern. Pattern being 1, and then you're
How
converting
can
that.
you and with a type? I don't.
You're creating.
Oh, you're getting the memory. Oh, you're putting it in memory first. Is that what you're trying to do? You're trying to get it in on the stack first and then compare it. So you get the memory address, you cast it to a char star, you dereference it, and then compare it.
There.
Is there any way you could draw that as a picture for some reason? Because I'm just having issues picturing it and figuring out what.
I buy what he's doing. I buy it.
I'm not buying.
So I don't buy that. All right. So
not in this economy.
Okay. So if something is little endian, it means that the significance, and you know what I mean, goes up with the address. Okay. So if I have a short, and so it's 2 bytes. So this is going to be address A, and this is going to be address A plus 1. Do we agree on that? The byte that comes second is 1 more than the, okay. So what we're wondering about is if we had a value of 1, in which of these 2 bytes would it be? So let me just draw it twice. A and A plus 1. We're wondering, will the 1 be here or the 1 be there? Okay, so that's what we're wondering. So what this code does is, line 17, which is the wrong function completely. All right, so line 22 here, so that's the pattern equals 1. Okay, so that did either this or it did this. We're not sure. So let's take the address. Let me spell this out. Okay, and that's a return. So here's the address of pattern. So that means pointing at A. So there's no question that the address of the short is its first byte in memory. So we're wondering what happens next. So we have the address, and now we're going to cast it to a char star. This is a short star, and now we cast it to a char star, which means we're only going to consider this. And if we find a 1 there, it's little endian. And if we find a 0 there, it's big endian.
Oh, so pattern is you're just, that's not like the bitwise and, that's the get the address of and.
Yes.
Okay.
How do you know?
You can't and with the type.
Yeah.
Well, bitwise and is a binary operator, and there's only one operator. There's only one operand here, so it must be the logical and.
By the
I'm sorry, it's
substitution
not. It
postulate.
must be the. It must be the take the address of.
So
Yeah.
maybe I'm just weird. Why don't we use a char in the first place? Why do we have to create a pattern and then transfer it into a char?
You need at least 2 bytes.
Oh, for yeah.
And
Yeah.
endianness is relationship between bytes, not within
Yeah.
a byte.
Okay, I see it now.
Okay. Cool.
You should run it and see what it returns, just for sanity's sake.
All right. I'll do that. Now it's true. So your version gave us false.
Nice.
Okay. Good. So there is so many cool puzzles I could give you for solving complicated things using only bit operations. And these are enormously fast. So solving something with no loops, no if statements is the way to go. Speaking of computer organization, did you know that an if statement of any kind massively slows you down?
Makes sense.
But do you know why?
Because it has
Okay.
to compare the two things.
No. So let me write down speculation. And another word, pipeline. So pipelining is a very powerful technique to greatly speed up the execution of your CPU. So the stages in the pipeline might be something like address computation, instruction fetch, instruction decode, operand, operand fetch. So there could be as many as 16, 20 different stages in the execution of one instruction. And what that means is when you have a pipeline CPU, it means you're not executing one instruction at a time. You're executing many instructions at the same time. In fact, as many stages as you have in your pipeline, that's how many instructions are in the process of being executed. So we might be fetching the address, fetching the instruction for one instruction, but later on in this pipeline, we're processing other instructions. And then at every clock cycle, the results from the previous clock cycle move forward by one stage in the pipeline. So what does this have to do with if statements? Well, in order to keep your pipeline full and going, the compiler will generate code that will speculate the outcome of the if statement. And if it guesses right, the flow through the pipeline, it goes uninterrupted. But if it guesses wrong, that means it has to flush all of the stages in the pipeline and load up, start over again, loading up a different set of instructions. So an if statement can be dramatically big slowdown because it may cause a flushing of all of your cache, all of your stages of your pipeline. Do you get the idea?
So how does it choose what to guess? Does it always guess like that's going to be like false or something, or is it a little smarter than that?
It would typically just guess at the true case. So it's conceivable that you can speed up an innermost loop simply by considering which sense of the if statement. So if you find that you're frequently guessing wrong, now the question is, how would you know that? I'm sure there is a way. I'm sure there's a tool that will tell you when the pipeline is being cleared. Just by changing the sense of the if statement, you'd be going faster. Better yet, maybe it's possible to eliminate the if statement.
Like how we use the compare statement in ARM, which is just a minus.
Well, the compare is the if statement, because the compare is going to be mated up with a branch. So what the CPU is going to be doing is the compare is executing now. The branch statement is behind it in the pipeline, and the statement after the branch is behind that in the pipeline. So if the branch is not taken, there we go. If the branch is not taken, then the pipeline continues without interruption. But if the branch is taken, we have to refill the pipeline. So that's the answer. If the branch is not taken, the pipeline will continue running. So you want to make sure that you, to get the fastest code possible, you want to organize your if statements so that the branch is taken in the less frequent case. Right? One of the great ideas of computer science is make the common case fast. So that's a lesson for you. Okay. Now let me expand this discussion to GPUs. So in a GPU, there are warps of 16 cores. So all cores in a warp execute the same instruction at the same time. All cores are in lockstep with each other. So GPU programs, let's call it in the case of a graphics, let's call it a shader. So the worst thing you can have in your shader is an if statement. Because within a warp, so we've got 16 of them, right? So let's say this one will evaluate to true, this one evaluates to true. They're all evaluating the same condition at the same time. This one is false, this one is true, this one is true, this one is true, etc. This is going to slow you down, and here's why. all of the cores that evaluate true will execute while this core is suspended. Remember, all cores have to do the same thing at the same time or be suspended. So all of the true cores continue on. And remember, it's an if statement. So the code block for the true case could be really long and expensive. So the false case could be suspended a long time. But when you get to the end of the true block, then all the true cores are suspended and the false cores run. And when the false code block finishes, then they can all move on together. So the worst thing you want in a shader is an if statement. In fact, if speed is such a concern, you might write different shaders, one for the true case, one for the false case. Just so that if you know in advance all of the what you want the outcome to be, true or false, then you could actually abstract out the if statement and just change which shader you use. It's that important. Okay. All right. So like I was saying, there's a universe of hundreds, thousands of tricks that you can do with bit twiddling. I encourage you to, for entertainment purposes, try to Google that. For example, let me fire up my browser here. And let's try bit twiddling hacks. How about the Stanford Computer Graphics Laboratory? Okay.
Ironic
Now,
that it's
these
for,
are.
I was going to
It's
say
what?
ironic that it's for computer graphics and the website is very boring and not really graphically pleasing.
Right. All right, so detect if two integers have opposite signs. Now, this is even fancier than the way we did it. They did it with an exclusive OR. Start assuming you have two signed values. If the exclusive OR is negative, it means that the sign bit was different in both operands. That's pretty cool. So absolute value without branching, because how would you do absolute value? If it's negative, make it positive. So here's a way of doing it without the if statement. So this is totally crazy. Just here's the power of 2, 1. Let's find conditionally negate without branching. So if statement without an if statement. Counting bits. Now this is the naive way. You want to know how many bits in a value are turned on. So you can count the bits by looping through all the bits and counting them. But then here's Brian Kernighan. He's got a loop. This one is by lookup table, but it means you have to have a lookup table. This one does have a loop, but the advantage of Kernighan's method is it only loops as many times as you have 1 bits. So for example, if it was a power of 2, this loop would run only once. Okay, this is fascinating. Absolutely fascinating. Now, where you are most likely to run into bit twiddling, it will be if you go into a field that uses embedded processors. So Raspberry Pi, maybe, Arduino for sure. So if you go into a profession that involves hardware, you're going to need to master bit twiddling. Okay? So let's move on to a completely different subject, shall we? Let's show a editor, and let's see, I think I'm pretty sure this is safe. At least I'm just in my home directory. So how about, I want you to code on your machine too, okay? Now, if you're on the Mac, you can use the terminal, but if you're on Windows, you have to use Whizzle. Okay, everybody? Or you could use your Debian, but it'll just be really slow. All right.
Wait, can't we use
So-
the VS Code?
Yeah, I'm using VS Code. I don't understand.
Yeah, never mind. I'm just messing things up as usual.
Thomas, don't do that. Don't do that. You know what? I hate it when you do that. I'll be really, really strong about it. What do I hate that you're doing? Is you're running yourself down. Let other people run you down. Okay.
But I don't want to get stabbed.
Yeah. No, but what I'm saying to you is that you know, have confidence and don't put yourself down. Nobody put yourself down. There's one thing to be like self-deprecating, but doing it too often is harmful to you. Okay, so have confidence. What was your question?
I was asking if VS Code would work because I forgot the context of some of the things that you were basically asking us to do. Like when you mentioned
Okay.
doing stuff in all these other programs, I thought that VS Code was not one of them for whatever reason.
No, you can edit in VS Code and compile and run on Ubuntu under Windows. Okay. Okay. So whatever it is, you can't be coding this code in Windows. It's got to be something that looks like Linux, either the Mac or Ubuntu on Windows, or even your ARM-based virtual machine. Okay. And oh, let me stick to my guns. Let's say I see int types. I really, as a preference, would rather use explicit types. Like I'll make it signed. 4. Okay. And let's just do some sanity checking. Let's say if count is greater than 32, let's just limit ourselves to 32. Okay. I is less than count, I plus plus. And the result So let's do man fork. All right, so from this, I'm getting that I need to include unistd.h. Okay. And let me read on some more. And it's a PID type. Okay. So PID type P ID. And okay. In fact, I'm going to leave this one out entirely because that we don't need that. And now return 0. Okay. So what's exciting here is the use of this system call fork. So let me compile this, make sure it works. What's it called? G++ fork test.cpp. So I got some expected. Oh yeah, well, I should add that last brace, shouldn't I? All right, so what do you think this will do? I'll just say 1, a.out 1. Okay, so I got a child and its process ID. What's a process ID? Every process has a process ID. In fact, every thread has a process ID. So what's a process ID? These are the things that I'm running right now. And PID, this is the process ID for each of those processes. Now I can make this smaller so that it's bigger on your screen. Are the characters getting bigger? All right. So now, so I ran my thing and I was able, what did I just do? I launched another process. So how about 16? Oh, you know what I did? Why, anybody know why? Help,
I did 12 and got something very similar.
what the? What? Oh, okay. You just have to wait now because this was an infinite loop for some reason. I equals 0. I less
Use
than count.
Control C to exit it.
Oh, I've done a lot of Control C's, believe me, but there were a whole bunch already queued up.
Mm.
All right, so what the hell went wrong here? Oh.
PID was made equal to 0.
No. Here, let me fix it by putting in exit because that was 16 squared. Actually, it was 16. Who knows what it was? 16 to a power. Run that. Okay, that works much better. Okay, so I just launched my program, became the parent of 16 child processes. Okay, so what just happened is the fork system call makes a duplicate of the current running process. a duplicate, except for one thing, the return value of fork. Okay, so one program, one process comes in and it does a fork. When fork returns, two processes return. And they are exactly the same, except for the parent will return non-zero and the child will return 0. That is the only difference between the two processes. Now, this is not making new threads. So these are processes. That means that as the parent continues on, its paths and the code and the execution is now completely divergent from the child. The parent and the child are now free to be completely different. Okay?
So they don't have the same address space?
Correct. Threads have the same address space, but fork creates new processes by copying the address space of the parent and then launching that copy as its own independent process, its own independent execution unit. The only difference in the address space is whether fork returns 0 or non-zero.
And when would it return non-zero?
Let me, well, I just showed you, but let me show you again. Here, okay. So let's put in chrono. Get some practice with chrono. And that means we'll also need thread. All right, and now here, I am child, blah, 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 starting. And that needs a space. And then I'm gonna do this thread sleep for chrono, colon, second 3. And then exit. Oh, I want to print out it. Okay, so you see what that's going to do? So the child will launch, the parent will move right on because it senses the process ID is not 0. Only the child will do those printouts. In fact, what I'll go here is I'll say, see out, parent is exiting.
So you're saying the child will sleep for 3 seconds? Is that what's going on?
Each child will sleep for 3 seconds. All right, let's run this.
Oh yeah, don't you want to have the exit so you don't have another infinite loop?
Yeah, what did I do wrong again?
You
That
forgot to
should
have
be
the
outside
exit.
the loop.
Or remember when you
Oh,
had
yeah.
the
Yeah, sorry. Exit 0. Thank you.
So the fork's gonna run in the background while like if we start this program, the fork isn't going to end until it's I don't know how to say that in English. Because like when I run the program, like right there, it starts and then the program ends and then it displays that it's end the processes are ending. So does that mean that like despite our code finishing, the processors are still running?
Right, because we're talking about a whole family of processes.
So how do we edit said processes then?
Edit a process?
Uh,
What does that mean?
I mean, how do we say like what they're how do we say okay, do this?
You say, do this. Please come up with a more articulate question.
I'm trying to figure out. So
May-
so basically, is each of these children, are they going to be running this code like a copy of this code that we just compiled and ran?
Exactly, exactly. I'm gonna
Oh,
make this longer.
yeah.
I'm gonna make this longer, and then let me recompile. And then here's one process being spawned. Now look, I'm in my shell. My program ended, and then at some point later, the child ended. It was running in the background.
So it's going to return a non-zero if I'm just maybe I'm not seeing it. When does it return a non-zero? When it's still running?
If you're the one who called fork. If you called fork, you're the parent, and you'll get back the process ID of the child. The child will get back a process ID of 0.
So basically, when you put that stuff in the if statement, you say, I want only the children to run this code.
Correct.
So how do we know that the child is running that like the see out statements and not like the parent?
This if statement will only be entered if you're a child, and it says I'm a child.
Oh, okay.
So let me put in, let's see if I remember. I'll do it here. Oh, no, that's get PID. Okay, so let's find out what the parent's process ID is, and you'll see that it's different from the child's process ID. Here's one child. Notice the numbers are different. They're different processes. Let me do a PS. Oops, I was too late. Okay, so let me run that again, and now do a PS. Ooh, there's 93,845. It's still running. And now it's gone. So is this starting to click for everybody?
It's getting there.
Fork is one process in, 2 identical processes come out, hence the name fork.
So
So
what's the time you would want to do this? Like want to run these two separate processes?
you're looking at it. You ready? On this line, it says that my shell is a program with process ID 28545. Actually, I'm going to do this a little bit more. I'm going to run the program, and I'll tell it to do 4 processes, and then I'm going to do PS minus L. I'm sorry, I'm going to have to make the window bigger. Now look at this. My shell is process ID is 28545. And it's a pretty small number, yes, compared to 93,000. That's because my shell was launched a long time ago. There have been about 70,000 processes that have come and gone since the last time I started my shell. But look at this. Here's all the children and their parent process ID is 1. Now the number 1 for a process ID is special. That means it's the first process. Where did the first process come from? In order to run, well, Joshua, let me answer your, put a period on your question. What was your question? Damn. What was your question?
I forgot I wasn't mute. I was muted. So what's an example of like sometime you would want to fork and suddenly launch all these different processes?
Yeah. So here I am. I'm in a process called a shell, and I want to run LS. LS is another program, right? So in order to do anything useful on the computer, I need to be able to launch programs. All of those start with a fork.
So you're basically just wanting to run multiple programs at the same time, hence using a fork.
Well, if you couldn't run multiple programs at the same time, then welcome to the 1950s, right? The only way to run more than one program ever is with a fork. It all starts with a fork.
So I guess, and so operating systems use forks a lot, right? In that case.
Mm-hmm.
Okay. I think a good question I have too is also when, like, I understand that the difference between, a fork and a thread are forks have a copy of the address space, but not the same address space. They have a copy of the parents. But I'm just confused, like, why would we use a fork over a thread or a thread over a fork?
Well, that's a straightforward question. If you want to have many execution units working together in the same address space, on the same code, on the same data, then you'll use threads. But if you want programs to work on different things without sharing address spaces, then you're going to use fork.
Okay, so with threads though, like, the program will not end until all the threads are done?
That's up to the programmer. So the programmer can choose that when the main thread exits, the child threads continue running.
So
Okay, go ahead.
Yeah, that makes sense. Another question I have is, when you fork, is there like a certain, let's say I have like 4 gigabytes of memory. Is there like, how does the computer split up how much memory each get? If that makes sense.
Well, you're gonna have to take operating systems.
Oh boy, okay.
That'll be next semester, right?
I don't think I can fit it in my schedule, unfortunately.
Well, you're gonna have to fit it in sometime. Mhm.
And OS is the next like big course that you need, that CS majors have to take, right? After this class.
For many catalog years, yes. For some, no.
Okay.
But going forward, that's true. So spring would be Comp Org, where you learn about a whole bunch of stuff, touching upon the remainder of the semester now is going to be touching on superficially subjects from operating systems. In the fall, you take operating systems where you go into those things in detail. Okay? Now, why should we cover the same material twice? Well,
Because
the
it's
material
really,
we're
really
talking
difficult.
about- yes, yes. And also, it's really, really important. The big thing that we learn in operating systems is parallel execution, either with multiple processes or with multiple threads. And that is one of the most important lessons a person graduating in the 21st century needs to master. Your mastery of parallel processing will mean the difference between you and another job candidate. Okay? There's a reason why CPU chips have so many cores, because the future is all in parallel processing. Morgan, Rebecca, any questions?
Right now, I'm just trying to get everything together in my head because it's like I'm just trying to process all of this at the moment. The hard thing for me that I'm getting stuck at is and you've gone over this at least twice already, is like these processes are going on at the same time, and the fact that they're different yet the same kind of thing. So it's like, is there any point in running the same thing multiple times?
Well, maybe there is. For instance, I could tell each child, let's say I was running a web server. Perfect example. I'm a web server, and every time I get a network connection, I fork myself.
That could be taken very poorly. But you likely create you create a fork so that you can have one new person log in, do whatever the heck they need.
Essentially, yes. And one of the reasons why I love teaching operating systems is I get to say a lot of outrageous things, and it's completely appropriate. So forking yourself is definitely one of the things that you do in an OS course.
I'm gonna take that out of context there.
Okay. All right. Now, let's see, sleep 1. Okay. So let me show you something else. Sleep 10, sleep 10, sleep 10, PS. All right, let me run those again, but PS minus L. Okay. Oh, those are still sleeping. The first set just finished. But what I want you to look at here is notice the process ID of my shell is 28545. And notice the parent's process ID of all of these children, sleep 10, sleep 10, sleep 10. They all have the shell, my shell, as their parent. So it was my shell that did the fork and then somehow convinced the child to change the program they're executing. That's the subject of the next thing in the course. So what I want you to see here, note here, is that this is an instance of what I showed you just now is an instance of the shell forking new processes in the background. That's what the ampersand does. So if these were semicolons, this is just shell syntax, it's going to do one, then the next, then the next. So this is going to be at least 30 seconds. And then when you do the PS, you won't find sleep at all. Come on.
Hasn't been 30 seconds yet.
Could have made it smaller numbers. Okay, so notice there's no instance of sleep because those were executed in serially, and the second sleep started only when the first sleep was finished. However, if we run them in parallel, and I'm going to make it 5 seconds each. Whoops, that would be even worse. What the hell, man? Now you'll notice in the PS output, which will happen immediately, you'll see 3 instances of sleep, all sharing the same parent ID. And 5 seconds later, they all finished. Okay, so here's a case where the shell, in order to get another program to run, the shell has to do a fork. There must be something else, because if all you could do was duplicate yourself, then we wouldn't be able to run any other programs. There must be a way of having a program decide to load up a different executable. And that is the next part of the course, which would be, so here we are, we're in the child, and let's, it printed out that it's the child. And what will I do? I think I'll use execl. All right, so char star /bin/ls and happy. Let's try that. Now here is a function call. It's a system call actually. Exec. Now exec is part of a really big family. So this is execl. I'll just quick pull up the man page for exec. That's not the right one. So how about man 2 exec? How about man 3 exec? Okay, there it is. So exec is part of a family. Execl, execle, LP, CV, V, VP, or V capital P. Okay. So there's the man page. Let's compile this. Come on, where's the compile? That's not a compile. There it is. Okay. Now, the last time I ran this, the exec wasn't there. So each process that was forked slept for 10 seconds and then printed out that they were ending. Okay, so let's see what this does. Just one of them. All right, so let me clear this screen and run it again, and let's see all the output. Here's the parent. The parent is running. The parent is exiting, having already launched a child. The child is starting, but then I'm getting the output of LS. So my child has been programmed to overlay itself with another program. So fork launches the new process within a copy of the parent's address space, but then the exec overwrites the address space with that of another program loaded from disk. You got it? Okay, chew on this for a while. Talk out loud, talk it out.
What I'm basically trying to comprehend this as is when we call a fork, we're essentially just going, okay, from here on, this is basically a new function call. Whatever happens, happens until it returns. And just until the program itself ends and it gets to main or has to exit for whatever reason. I'm guessing that
When
based
you
on
call a fork, one process calls fork, but two processes return from fork. They are completely independent of each other, except when they start out, the address spaces are copies of each other, with the exception of the return value of fork. So when a forked process exits, it's a program that terminated. When so two processes, well, I'm sorry, one process calls fork, two return, but there is no return value for exec. Okay, so let me replace this now with the following. The error. Okay, you should never see this. Let's try it again. Okay, and you don't see it. Something really bad happened. It's not printed because when exec does not return. When exec is finished, you're a different program. So tell you what, I'll force that statement to be printed by putting in total garbage here. So there is no program named that. So let's run, let's compile and run. So exec did return because it couldn't launch the named program. Does that help?
kind of, so if it calls a program that doesn't have a return, then it's just going to go into that program and terminate itself.
I don't know what you mean. So I don't know what you mean by a return. Return is irrelevant here. We're not talking about returns. If exec fails, you're still in the child. If exec succeeds, you're still in the child, but you're running a different program.
Okay, so it just like goes into something else on its own.
Okay. Okay.
Basically, like if exec succeeded and it came back and there was, and C error wasn't there, and instead you had C out, blah, 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 it would print something, correct? And then it would go to exit and then terminate.
No.
Yeah, well, the C error is the same as C out, right? Just going.
What
just,
exec
yeah,
does
and-
is replace the child process's address space. It's executing completely different code.
Hmm.
Everything after exec, if it succeeds, is gone. It's nuked. It's not done anymore.
Okay, that's Cephas has got it right. So here's the parent process, and it has a variable called I, and it's set to value 31. And then it does a fork. Well, that means a second address space is created. It has an I, which is 31. but this is the child. Thereafter, the child can do whatever it wants. It's going to diverge from the parent immediately after running the coming back from fork. So when the exec happens, of let's say /bin/ls, what's happening there is this box remains. That is the executing process, but the address space is then overwritten with ls. So it's the fork that creates the address space, the container. Exec alters the contents of the container. Okay, so we're coming up against the end of the class. Who's got a question?
I think Cephas might have had a question that he wanted to ask from the comp sci chat.
Oh, from this chat? What mean comp sci chat?
The comp org chat in Discord.
I'm supposed to be monitoring that too?
I was more saying that Cephas might poke out and say, "Oi, thingy."
Not currently, but in general, yes, I think you should.
Okay.
Anyway, I'm having a specific issue with partitioning the threads for neon execution because everything has to be divisible by 4 for the neon instructions. If you split size, every single section you give to a thread has to be divisible by 4, or else obviously it works in units of 4. And in general, there doesn't seem to be a nice way to do that.
In general. So what I told you to do in this course is in this project is a subset. It's not the general case, right? Correct?
I don't really remember reading any
Okay.
sort of
Well, let me see.
caveats, but maybe.
All right. So here, suppose this is 8 floats long. And so that's a multiple of 4. Great. So let's divide this onto 4 cores. That means each of the 4 cores is only going to get 2 floats. And now all of a sudden the program is going to fail.
Because doesn't the thing call a minimum of 4 floats?
Right. The instruction that we're using requires a minimum of 4 floats. It requires exactly 4 floats. So you can't use 8, can you?
No.
You'll have to expand this up to the next boundary of 16. This is a specific way of handling this problem. But you asked about a general solution. So let's say you had, so let me give you a different hypothetical. Let's say you had 19 floats and you have 4 cores. So you can do 4 on these and 5. We're not talking about SIMD anymore. We're not talking about the 4 floats.
Okay, so I have this version for the general case. That one's reasonably easy, but the neon one is kind of annoying. What if you I manually switched our VM to run 3 cores so I can test it out. But with that one, because usually when you divide it, the numbers you get won't be divisible by 4, and then you somehow have to do a random optimization problem for each one, and I'm not sure how you.
No, just you have your figure, you have your neon instruction that requires a multiple of 4 floats. And then you have your number of cores. Isn't there something having to do with a least common, multiple, least common?
So you're just saying
So-
manipulate size until they are equal, such that you get a
Manipulate
reasonable
size.
value?
Yes, manipulate the size until you get values that will work. So in the 2 core, if you make everything by 16, divisible by 16, it's all going to work.
Yes, the 2 core is trivial. So,
Right. So you
like,
wanted
if
to
you
do
have
3 core, and I admire that. So I admire the fact that you wanted to try it with 3, but it seems to me then that the number 12 is going to be important to you.
yeah, so we just have to manipulate. So we are going to change. And if we change size, we'd have to change size for all of them as well. You'd have to do this check before running either of the
Yes,
test
the
cases.
spec says that. The spec says that.
The spec was a little bit vague about specifying this particular problem. At least I couldn't read it very well.
Mm-hmm. Okay, well, I'm open to amending the spec for a future class. If you want to email me with a specific area you think I should address further.
You addressed it, but I think you were trying to like make it where we figured it out for ourselves, but it was.
And did you?
I'm asking this question, so no, not really.
All right, well, you're getting closer to the answer. All right, anyways, class is over. Maybe I'll see you tonight because you have a project due. See you tonight on
See
the
ya.
Discord. Okay, bye-bye.